So we have 3 pump arounds. So first pump around, the drawing stage is 5. So return to 4. 5, 4. So it is 5. This is 4. The flow rate is 387,500. 387,500. And the temperature is 107 degrees centigrade. At this temperature, it is returned to the stage 4. Similarly, you add the second pump around, which is at stage 12. So it is drawn from stage 12 and given back to stage 11. So stage 12 and stage 11, the flow rate is 235,300. 235,300, and temperature is 205. Okay, so it is returned at 205 degrees centigrade. Then we add the third pump around, and that pump around is from 18 to 17, stage 18 to stage 17. So 18 to 17, the flow rate will be 2300 and temperature is 220. 2300 and 220. So that's how we set the pump around information of the atmospheric column. Now we come to the stripper. How many strippers are there? We have 3 strippers. So first stripper, S1, how many stages are there for that? There are 4 theoretical stages. So we have 4 theoretical stages, and we draw the liquid from 7th stage and we return it to the 6th stage. So we draw it from 7th stage, return it to 6th stage, right? And we have the stripping steam information. So stripping steam, we have 1500 kg. Now we do not have any option to give such information over here. Why? Because we have not added any extra steam. So we go back to the flow sheet. In the flow sheet, we add this steam. So this is stripper steam feed. So stripper steam 1. Then suppose there are 3 strippers, okay? We use these icons to identify the stripper 1, stripper 2, stripper 3. So this is the stripper 1. Let us say this is steam for stripper 2. And finally, this is for steam for stripper 3. Okay, and this is the bottom product of the stripper. Now this one, let us name it as H naphtha, because the first stripper, it takes out heavy naphtha. The second side stripper, it takes out the kerosene. So we put it over here. And name it as kerosene. And third one, light gas oil. So we write it as light gas oil. Okay, so that way the inputs and outputs from the strippers, they are fixed. Now we won't have such problem. You see the stripping stream has been on now. It is activated. So ST1 is the steam input for the first stripper, which we are working with. And the bottom product, it is 27,500 kg. 27,500 kg. Now this is how the first stripper has been fixed. Now let us enter the new stripper, and the new stripper, again, number of stage we have 3. The stripper product is kerosene. This is kerosene. It is drawn from 14th stage, returned at 13th stage. So 14 and 13 are inserted. Stripping steam is ST2, and the bottom product is 34,300. So it is 34,300. So that's how we enter the second stripper. Now we come to the third stripper. The third stripper, the number of stages 3, and stripper product is light gas oil. Liquid is drawn from stage 20, returned at 19. The stripping steam is ST3, third stripper, and the bottom product is 76,000 kg per hour. So it is 76,000 kg per hour. So this much of light gas oil is being taken out from the column. Okay. Now let us run the simulation. Before that, we have to enter this information over here. We have entered ST1, ST2, ST3, right? So this information we have to provide. So what is ST1? ST1, steam, 400 degrees centigrade and 3 bar pressure. The mass flow is 1,500 kg per hour. So it is 1,500 kg per hour. ST2, it is again 400 degrees centigrade and 3 bar pressure. So this information is universal. The steam temperature and pressure in the entire process are 400 degrees centigrade and 3 bar. Only the flow rate will change. So in this case, flow rate is 600 kg per hour. So here it is 600 kg per hour. And finally, this is 400, 3 bar, and mass flow rate is, it is 100. 100 kg per hour of steam. Now required input complete, and we can run the simulation. So we can run the simulation. Let us run. Yeah. So it has now run, and the simulation results are all available. So let us see the simulation results. This is the result summary. We have streams over here. These are the streams, right? You can find the temperature and pressure of each and every stream. and the mass flows. Some of the mass flows we have fixed. For instance, what should be the mass flow rate of heavy naphtha? So heavy naphtha is 27,500, kerosene 34,300, the light gas oil. So these are the information we have given. So as per that information, it has done the calculation. Now, what we need to find out is what are the rate of these pseudo components. Okay. So pseudo components 87C, the flow rate is 16.3852 kg per hour. That means 16.3852 kg of heavy naphtha will boil at 87 degree centigrade. So that's what it means. Now we have to find out the ASTM 86 curve, right? So what we need to do, we need to find out the temperature and flow profiles. Temperature and flow profiles we can get from here. So this is the profile. So this is the temperature profile. So you can see the customs, temperature profile, flow profile. Okay. So these are the temperature and flow profiles, right? So how the temperature and pressure they change from stage 1 to stage 25. You can see over there. And compare the calculated ASTM D86 curve of the atmospheric column products with experimentally measured distillation column. Experimentally measured distillation curves are given over here. I mean, curves are not given, but boiling points are given. But we have to find out the calculated ASTM D86 curve. But ASTM D86 curves have not been calculated. They are found over here in stream results. In the stream results, these volume percent curves are not activated. For that, we have to go to the setup. There we have report options. In the report options, we go to the stream. In the stream, we have property sets. And only these property sets are provided, but we have to add a few. We add these gas property sets. Then we have petro property sets, thermal, and T export. Anything else? Light, kindle. I think this will be enough. So once we do it, we run it once again and go back to our stream results, and you will find volume percent curves are activated. Okay. So go to the volume percent curves. You will find them. Now here you will find the curve view. Our interest is ASTM D86 curve. So we fix it over here. ASTM D86 curve. Now let us compare it with, say, H naphtha. Okay. Now H naphtha, we use custom stream volume percent and H naphtha. Put OK. Right. So you can see how the temperature is increasing. The temperature is from 130 to say 197. Okay, so this is the range. Now here H naphtha, it is from 106 to 179. But here we have 130 to 197. So if you compare, I think the ASTM D86 curve calculated by Aspen Plus is not entirely matching with the experimental data. Obviously, because we have done the calculation with minimum information given to Aspen Plus. So it has done its best. Let us do it with kerosene. So for kerosene, we have this one, right? So this is the kerosene. So we write kerosene. So it is 180 to 267. It is 180 to 257. So kerosene is matching, you see. So this is the experimental curve. The minimum is 180. Here also it is minimum 180. And maximum it is 257. It is around 250. So kerosene is matching. Okay. So this information is matching with the experimental data. Right? So that's how you compare with the experimental data with Aspen found information. Okay. Now we continue our job. This ATM bot, this has to be inserted into the second column, which is the vacuum distillation column. So again, we bring in the petrofrac. Now this time we will not use the same icon. We will use a different icon. So let us use, say, we do not use any stripper. So I think this will do. We have a furnace, so we will use this icon. So it is vac call. Okay. Now this one is the bottom product. So we write vac bot. This is vac vap. This one we will connect it to the main feed, which will pass through the furnace. And we have another inlet that is about the steam. So we write vac steam. Now in this case we have three side streams. So side stream 1, side stream 2, side stream 3. So the side streams are here, side product from the main column. So this is side stream 1. This is side product 2. Now we do have names, right? What is side product 1? It is light vacuum gas oil. Side product 2 is medium vacuum gas oil. So we write medium vacuum gas oil. And third one is heavy vacuum gas oil. Right? And this one we change the name to light vacuum gas oil. Right? Okay. Now, these are the things that we need over here. So vacuum column, we do not have stripper, but we have pump around. Those information we have to provide. We have an extra stream. We have the extra stream of vac stem. So vac stem information that we have to provide. The steam, it is 400 degrees centigrade and 3 bar pressure, and the flow rate is 5000 kg per hour. So we write 5000 kg per hour of steam that is given to the vacuum column. Okay, so all the stream informations are there, and we have to provide the information of vacuum column. Number of stages, it will be 11, right? 11 theoretical stages. Condenser will be partial vapor, so it should be partial vapor. There is no liquid distillate over here. There is no reboiler. Valid phases are this. What is the distillate rate? Distillate rate will be 7000 kg per hour of vapor. So it is 7000 kg per hour of vapor that we have to provide. The streams, the ATM bot, it will go to 11th stage through the furnace, and steam also is provided on 11th stage. LVGO, the light vacuum gas oil, that is taken out of stage 3. Medium gas oil is taken out from stage 5, and heavy vacuum gas oil is taken out from stage 9. So 3, 5, 9. So we will put it here as 3, here 5, and here 9. And all of them are mass flow rates. Those informations are there with us. So here we have 5000 kg per hour, 5000 kg, and 250 kg. So it is 5000, 5000, and 250 kg per hour. And all those gas oils will be in liquid state, right? So we put it in liquid. That way streams are all set. Pressure. The column pressure, they are top and bottom pressures are 0.1 bar and 3 bar respectively. So it is 0.1 bar and this is 3 bar. And finally the furnace. Furnace temperature, it is 380 degrees centigrade and 2 bar. So 380 and 2 bar respectively. We have to provide the pump around information. So pump around information is over here. So it is first pump around drawn from stage 2. So let us give this information. First pump around drawn from stage 2, returned at stage 1. And the flow rate circulation is 35,000 kg. 35,000 kg per hour. And here we have to provide the temperature change. Okay, temperature change is 35 degrees centigrade. Actually, it should be minus 35 degrees centigrade. So temperature change, we have to provide over here. It should be minus 10,000 to 0. Specified value must be negative. So temperature drops. So it is minus 35. Okay. Then the second one is stage 4 to stage 3. stage 4 to stage 3, the flow rate will be 1,20,000 kg per hour of circulation. So 1,20,000 kg per circulation, and temperature drop is minus 20 degrees centigrade. And finally, the pump around 3 that comes out from stage 9 and returns at stage 5. So 9 and 5. The circulation rate is 25,000 and temperature change is again minus 20 degrees centigrade. Okay. So the second one also, let us check. Here we have done a mistake. It should be temperature change, which is minus 20 degrees. Right. So be very careful about choosing the correct information over here. Okay. So anything else that we have missed out? No, we have given pump around, we have given side stream, we have given all those information. So okay, now we are ready to run the simulation. So run the simulation once again. I hope it converges. Yes, it converges very soon. And we got the result. So let us see the stream results only for the vacuum column. So we are not interested to know about the atmospheric column. We have already seen all of them. So let us close these ones. Okay, so these are the information of vacuum column. Okay. So what is the flow rate of HVGO? We have set. So we have got 250 kg per hour, 5,000 kg per hour. But the bottom flow rate is very high. Right? So bottom flow rate is very high. The vapor flow rate is 7,000. Okay, whatever it is, we are interested to find the ASTM D86 curve of the vacuum column product. So let us go to the volume percent, and the products are over here. So let us choose LVGO, MVGO and HVGO. They are the vacuum column products. And we have to find the ASTM D86 curves for them. So okay, so these are the ASTM D86 curves. This is the stream's volume percent from 0 to 100% and how the temperature changes over these cuts. Okay, so that's how we solve the problem. Okay, so that's how we perform the petroleum fractionation in Aspen Plus. I hope you have enjoyed this lecture and learned many things. We will come back with yet another interesting lecture very soon. Thank you.